theme on time-varying optimization, but now including feedback, connecting better to Florian's talk. So this was by Emiliano Dall'Anese. He got his PhD from University of Padova, and he has been with NREL before joining recently University of Colorado. So he was leading on a very interesting R&D project at NREL.
Thank you, Steven, and thank you for the invite. It's very nice to be on this side of the ocean and in front of such a great audience. So as Steven said, we will continue the main theme of online algorithms, and the particular focus here will be on real-time decision-making tasks, where the term real-time will hopefully become a little bit more clear down the road. We can target applications such as real-time multi-parallel flow, real-time response, and so forth, but I also want to mention that a slight modification of the algorithms that we will see can also be applicable to other tasks, such as real-time control of wind farms or even other infrastructures such as water networks, or to control the overarching cyber infrastructure for the future grid. Anyways, in terms of outline, I will be partitioning the talk into parts. I will first focus on time-varying convex programs, and then I will dive into non-convex programs, such as the SCOPF. Let me also acknowledge my main collaborators, Andrea, who you already know by now, Tang and Steven, as well as Andrea Bernstein from NREL, formerly at EPF with Genève. Okay, so let me also first give a sample of works in context. Many people have been working on time-varying optimization, starting with Popkov, and then there is a seminal work of Andrea. Less works are present in the context of time-varying non-convex optimization. And of course, there is a huge amount of work in terms of regret analysis. But here, we're going to be looking at something a little bit different than regret analysis, mostly because I'm interested in linear convergence analysis of online algorithms, something that Andrea already nicely introduced. By the way, the idea of feedback-based optimization was also studied by Steven back in '99, other folks in Singapore in the communication system context, and then I left a big slide for power systems because there are so many good people who are working on these problems. Let me just say that this will become more clear. In this talk, I will be focusing on measurement-based online optimization. There is also a line of work on algorithms that are effectively utilized as feedback controllers, something that Florian explained in the first talk. Now, in terms of power systems, sorry, this is an ugly slide, but I wanted to acknowledge everybody. Actually, the work started back in 2009 with Jokic, who looked at a so-called KKT controller to solve in real time an economic dispatch problem with measurements of output powers of the generators. Then also, of course, Steven in terms of frequency control, right? And the first online algorithm was actually proposed by Genève, right? Comelec, if I'm not mistaken, where he considered a time-varying, unconstrained problem, and it worked beautifully. Now he has a startup, right? Then Andrea and I consider a time-varying problem, a convex problem. We use voltage measurement and we prove linear convergence. And today I will be mainly focused on this work, and then I will move to non-convex programs. Okay. Now, what is this feedback-based line optimization? So maybe this is a bit redundant, but since this is after the break, let us take a look. So I'm considering a time-varying map F that maps a vector U of control inputs into a state which is denoted by this vector Y. And I also have a vector of exogenous inputs or disturbances Y. So in Florian's parlance, this calligraphic F can be the power flow manifold in a sense, okay? Now, what we do, we associate with this time-varying map a continuous time optimization problem. Here, similarly to Andrea, I have the T, which is the temporal index. And you can think of a situation where I'm minimizing a cost function that evolves over time. This can capture distance from voltage stability limits or other socioeconomic objectives. You can think of time-varying constraints that here are generically denoted by G of Y, where you can think of moving the network output towards a given target that varies over time within a given error nu. Okay? Or time variability can simply be given by inputs to the problem. For example, this is a plot of the real power output from PV systems in Arizona, very close to ANA. Okay, nonetheless, if you think that you have infinite computational capability, and you can solve this problem here infinitely fast, then what you get is an optimal trajectory for your control actions U star, right? And of course, also an optimal trajectory for your network output Y, okay? So the problem statement here is actually very simple, and it is the following. How do we drive the output of our time-varying map towards a trajectory that continues to evolve over time? This is a problem statement. Now, in a traditional batch optimization setting, what we would do is to take a sampling interval, age, and sample the problem over time, right? Now, this age can be nothing but the interval that it takes for me to receive a measurement from the system, can be, let's say, an interval over which the problem is constant over time, but down the road we will see that this is nothing but the time that I require to compute an algorithmic step. Nonetheless, I sample the optimal trajectory, thus ending up with a sequence of static problems, right? And therefore, I can use all my toolboxes, and I can use any algorithm where a time step k, here k denotes the sampling index, okay? At every step, at every time k, I run a given algorithm that here is succinctly summarized with an operator t until convergence, right? And then at convergence, I spit out my optimal command, uk star, then I send down to my system or network, okay? Now this may not work because of computational limits. If my sampling time age is too small, if I want to spit out a solution every second, but I have an SDP that takes 1 minute, I'm in trouble, right? But also because perhaps I don't have capability to collect measurements sufficiently fast, measurement that translates into problem inputs, right? So to bypass this hurdle, a lot of people have looked at online optimization, right? So here I have a nested loop where at every time step I compute a number of algorithmic steps to spit out a solution. On optimization I compute one algorithmic step, I collect new inputs, and I go ahead another step, right? And again, there are many people who are working on that, and if you design the map T, the K, in a proper way, you may be able to track this optimal solution. What is the problem in a power system context? That this is a feed-forward control method, right? So if you don't know very well the map F, or if perhaps you're not able to collect the exogenous inputs at every time step, you may actually diverge, right? This is something that we don't want to have, since we are talking about power systems, right? So the idea of feedback based on optimization is actually very simple. Why don't we just measure the network output, and then we appropriately modify the algorithmic steps to include these measurements. So we adapt in real time to time-varying network conditions, and we are cognizant of the current state of the network. Of course, we cannot, besides Y, we can also measure constraint violation, and we can also measure actuation errors. And I will elaborate further on this point and try to connect with what Florian said. Okay. I hope that at least the philosophical setting is settled. But again, what I want to do is not to do a regret analysis. I want to have some sort of a stronger result in terms of tracking capabilities, which is somewhat related to input-to-state stability in control theory. Now, let us look at a bit of the math, and then we can look at power system examples. So let us consider a very generic problem where I want to minimize a cost functions associated with the network output. This can be voltages or power substation. We're going to see some examples. And a cost function associated with my control actions. And both of them, again, evolve over time, okay? And then we have some implicit constraints, which can model hardware constraints, and some constraints we can afford to dualize. Now, we're going to be considering a very first case, a convex case, nice and easy, where the map is linear, okay? And we have convex cost and constraints. Then we're going to be looking at the second case, where we can consider a generic nonlinear smooth map, like the power flow manifold, and generic, not so generic, cost and constraints functions, okay? And I will explain why not so generic. Nonetheless, we're going to utilize a common approach, which will involve a regular Lagrangian function, a primal-dual gradient method, so we're after first-order methods, and we're going to leverage contraction arguments to prove convergence. Okay, and I will be considering discrete time algorithms. Now let's start with the first convex setting. But first, let me introduce some notation. So all of you might know the Lagrangian function, which is again time varying. K again is the time index, where lambda is nothing but the vector of dual variables associated with this constraint that I can afford to dualize. And then hereafter, I will denote with zk star a KKT point of this problem here at time k. So if this creature here is convex, that this is nothing but a globally optimal solution at time k. If this creature here is non-convex, well, this is nothing but a critical point. Okay? Now, I play the first trick, without which I'm not able to derive any result, which is the following. We're going to be considering a regularized Lagrangian. R stands for regularized, where I add this strongly concave term in the dual variable. This is critical in order to prove linear convergence, results similar to what Andrea showed, but unfortunately we're going to perturb the set of KKT points of the problem. So this is a price to pay. We gain in tracking performance, we slightly pay in suboptimality. Okay? Okay. The last quantity that I introduce is this sigma k, which measures the temporal variability of my problem. This connects also to what Patrick was mentioning about let's say volatile ambient conditions and low conditions, or switching in the network. And this is nothing, but I take the norm of two consecutive KKT points, and then I just multiply by the inverse of my sampling time. So in the limit, for h that goes to 0, like in Fourier setting, this can be a proxy for a gradient, let's say, or a drifting coefficient, as Stephen calls it. Okay, let's look at the convex. So there is a set of assumptions that unfortunately we need to add, because this is not a panacea. There is something that we need to pay. So first of all, we're going to be working with convex and compact sets that we keep implicit. This is okay, because for many devices like PV systems, batteries, these are nice and convex and compact. We're going to be working with functions that are continuously differentiable with a Lipschitz gradient and also a bounded gradient. We're going to start with a strongly convex cost, but this is not a problem. And we're also assuming that the problem is feasible at every point in time. Otherwise, if the problem is not feasible, there is nothing to track, right? Now, let us take a look at an online implementation of a primal-dual method, okay? But there's nothing but the sequential execution of these two operations, where I update my vector u, right, by taking the gradient of my regular Lagrangian. Alpha is the step size, and then I project back into my implicit set, okay? And hopefully this projection here is easy to do, okay? And then I do something very similar for the dual variables, where D is a properly crafted compact set for the dual variables. Now, if I add my regularization term in the Lagrangian, then I'm in a good shape because I can show that these two operations are in fact a strongly monotone operator that is also Lipschitz. And based on the mathematical structure of the Lagrangian, I can also compute the Lipschitz constant of this operator. And then I'm in good shape because I will be able to leverage contractive arguments to prove linear convergence. This is where the trouble comes. If I consider the traditional Lagrangian, well, this guy here is a monotone operator, but not strongly monotone. So there is no way in the world that you can prove linear convergence of online algorithms. The best you can do probably is to do a dynamic gradient analysis. So when we go from static to line optimization, this is something that we need to be cognizant of. Okay, let us expand a little bit these terms to take a look at what are the mechanics behind this algorithm. And don't look at all the math, just focus on the blue term. And let us take a look, for example, at the dual ascent step. So here, in order to update my dual vector at time k, I need to evaluate my constraint function g at the current presumed system output, y. Because if you remember, h u plus dw is my network output, right? Now, and I do the same in the primal step to compute the Jacobian of my constraint function g, and also to compute my gradient, the gradient of the cost function C0. So now you understand why this leads to a feed-forward method, right? In fact, any online optimization algorithm is a feed-forward or autonomous system that is based on a network map and is based on us being able to collect proper information on the vector W. And I will make a connection in power system, and we will see that collecting the W is actually problematic in power systems. And I just said that it's model-based. So what is the idea behind feedback-based or measurement-based on optimization? It's actually very simple, almost trivial. Why do we need to utilize the map? Let us replace the map with measurements, right? So in this case, I can just replace my map with a measurement, and I can start evaluating the gradient and the Jacobian at the current measured network output. And if possible, for the dual step, I can just measure the constraint violation. If you remember, I had a constraint g of y less or equal to 0, therefore this is nothing but the constraint violation, right? Here, we don't need to collect the vector of exogenous inputs. I will give you a hint. This is the vector collecting all the non-controllable powers from secondary transformers. And we don't need to know the map, because the map comes for free from the measurements. Okay? Now, we end up with a, let's say, closed-loop system where we have algorithmic steps that are modified to accommodate measurements that may deviate from the postulated model. So, and on top of that, we have an online implementation. So we need to investigate the convergence properties, right? Or stability properties, right? So the first thing that we did in this work was to introduce some assumptions on the measurements. And one assumption that we introduced was the following. We said that if we take the model that you postulate and you take the measurement, then the discrepancy is bounded by a given constant, EY. Sorry. Okay? So we have a bounded noise model. Now, is this realistic? Well, yes, right? Because if I look at quantization errors or measurement errors, it's bounded. I will make a comment on the Gaussian error now soon, because I see that Anna is looking at the Gaussian. So, can capture modeling mismatches and also actuation errors. Here is one connection I want to make with Florian. So Florian had an epsilon, right? So if you have a sufficient if sufficient timescale separation between the local controllers, local regulators, and the speed of execution of the algorithm, then you're in good shape. And this EY can be a function of the epsilon differential. Okay? So now, based on this assumption, we can bound the error EP and ED that we commit in the computation of the primal and dual gradients. Okay? So here a bounded error translates into a bounded error in the computation of this guy here in the Hessian, and in computation of this term here that is in fact the gradient of the Lagrange with respect to the dual variable. Okay? So based on this intermediate result, then we have the main convergence result, which is the following. I don't know why it is yellow, sorry. So if we pick the step size of our algorithm, alpha, in a way that this funny looking inequality is satisfied, where R is up to us, because it was our regularization parameter, M is given by just looking at the cost, is the strong monotonicity coefficient, and L map was the ellipsis constant of our primal dual operator. Then we have the following result. If we look at the difference between our optimal, now we are in the convex case, so our optimal, globally optimal trajectory, zk star, and the trajectory that our algorithm spits out, zk, then this difference is bounded asymptotically. And the bound depends on the error that I commit in the evaluation of the primal dual gradients. It depends on sigma, which is nothing but the maximum drifting of my optimal trajectory, right? So this connects to what Patrick was saying. If I have something that varies abrupt over time, well, I can do the best that I can, but I may not be able to track it, right? If I have something nice and smooth, I will have a very tight bound. And also depends on K, which is the price that we need to pay for using a regular Lagrange. In fact, there is an R here. If you put R to 0, K goes to 0, right? But it's something we can do, because if R is 0, you're not going to be able to derive this result. And finally, rho of alpha is nothing but a contraction coefficient, which we need to enforce to be strictly less than 1, and this is given for free if this inequality here is satisfied. And this is something we can compute based on the mathematical structure of the problem. So you give me a demand response problem, we can compute rho of alpha. You give me a COPF, I linearize it, I'm able to do it. For the full-blown nonlinear, we will see that it's not possible. So now, actually Florian has had a nice intuition when we talk about this, and he said that this result here can actually be interpreted as an input to state stability, right? Bounded measurement error or actuation error, bounded deviation from the optimal trajectory. In signal processing, this can be nothing but a tracking result, right? Anyways, let's forget about convex programs for now, and let's dive into the non-convex setting, where we start considering a nonlinear but smooth map, and we can consider generic non-convex functions. Not so generic, because unfortunately we need to assume that they are twice continually differentiable. Why do we need to assume that? Because otherwise we were not able to prove convergence. So these are this is what we were able to do. So again, these are slightly stronger assumptions relative to the convex case. Convex case, I had the differentiable with ellipsis gradient. Here is twice continually differentiable. For now, we need to assume that we have a Lipschitz KKT trajectories, so no jumps for now. And also we go from a Slater condition to something a bit more convoluted. We need to assume a generalization of a Mangasarian-Fromovitz constraint qualification, where this is nothing but the normal con operator with respect to our convex and compact set U. And if you put this one to Rn, then you get the traditional MF constraint qualification. So this is just a technicality that ensures that there exists at least one KKT trajectory, and this is something that we need to live with. Okay. Now, the algorithm, surprisingly, is actually the same. So I'm going to show it here. It's the same. The only thing that we did was to add an additional parameter, eta, in the dual step for admittedly mathematical simplicity. And also something that we had to do was to work a little bit with a different definition of the norm. Instead of the norm 2 that I showed before, we're working with this particular norm, okay, where we scale down the weight of the dual variables with respect to this algorithmic parameter. Again, this is something that we had to do to prove, to get some analytical results. So now I will be focusing for a moment on the, let's say, measurement-free algorithm, because there were actually no results in the literature even for this case, for non-convex programs. And then I will try to make a few comments on how to add feedback. Okay? And then finally we go to power systems. Now, for this particular algorithm, there is something, the condition is a bit convoluted. So let me just try to add some intuitions. So everything can be reduced to a simple, supposedly simple inequality, where I have something that depends on delta, and I will tell you what is delta, and then something else, right? So if I spell out this term, and I'm not going to explain them, they are very complicated. They're very complicated, but after a few months, we realized that all this math can be explained with one sentence. And the sentence is the following, that if you look at a KKT trajectory, okay, so the cost function is, the Lagrangian is locally strongly convex in a neighborhood of the KKT point. So strong concavity comes for free from our regularized Lagrangian. Then we need to add this technical condition to ensure that it is also locally strongly convex. Why do we do that? Because we want to have a locally contractive region around the KKT trajectory. And then this delta here is nothing but the radius of our contractive region. Okay? So for the convex case, this came for free by assuming a strongly convex function. Here we need to add some more sophisticated conditions. And this is the case, by the way, for the COPF that we will see soon. Interestingly, this concept was related to the notion of strongly regular point that was introduced by Donchev, Valiev, and Rockefeller in 2013. And interesting enough, this is also a sufficient condition for the KKT trajectories not to disappear and not to bifurcate. So we have KKT trajectories over time that do not intersect or bifurcate. This is a limitation of this work. Bifurcation is something that is very tough, but we will try to look at that. Anyways, let's look at the theorem. So suppose that this condition holds, and suppose also that the algorithm starts inside the locally contractive region. Then the algorithm will be able to stay inside the locally contractive region and will be able to track a KKT trajectory ZK star. And in this case, the difference between our KKT trajectory and the iterates that our algorithm is producing is bounded. And it's bounded by something very similar. Again, rho alpha n is a contraction coefficient, which is strictly less than 1 by virtue of this condition that we impose. And k prime, again, is the price to pay for using a regular Lagrangian. Okay. And yeah, I forgot to mention that these conditions here also implicitly encapsulate the existence of a set of algorithmic parameters that ensures that the algorithmic step is a contraction. Okay, so intuitively, what is this saying? How is an algorithm able to stay inside the contractive region? So let us take a look at this figure. So we are at this point here. This is a KKT point at time k. and then I have a contracted region of radius delta. Okay? Then the problem is changing over time. It's following a trajectory, Lipschitz trajectory, and it lands here at the next sampling time. So zk plus 1 star. And then I have another contracted region that is inside, that is around this point, which now I'm assuming for simplicity the same radius. Then if I pick this point here and I take a ball of radius that is given by the contraction coefficient at the maximum variability of my problem, then this ball has to be included in the intersection of the two contracted regions. So this is a sufficient condition for the algorithm to never go outside the contracted region of the KKT trajectory. But anyways, let us just take another look at how to include measurements, and then we look at power system examples. So it is actually very simple. The philosophy is the same. Here I have a constraint that is evaluated at the current network output, and therefore I can just measure it, right? So if this one is something that measures how much the voltages are outside my bounds, I can just stick it in here, right? And then we are also trying to replace here, include a measurement of the Jacobian. Did we do that? Yes and no. We prove linear convergence for the case where we have a generic nonlinear map and we have linear constraints. There are some preliminary results for the case we have generic nonlinear constraints. Again, the simulations work, the theorem is not there yet, but hopefully next year. Okay, so let's dive into an example of application, and to diversify with respect to the other talks, let us take a look at distribution systems. Okay, so we consider a distribution system. This is a substation, and every green point bullet correspond to a DR, right? A PV inverter, a storage system, electric vehicles, and so on and so forth. So surprisingly, there is a one-to-one map between the math that I showed a few slides ago and this application. And the map is the following. So U is a vector collecting all the set points of the controllable devices. So UI, which is associated with the ith device, is a 2x1 vector collecting the active and reactive power set points for that device. And this guy here, we collect hardware constraints. The W is a humongous vector that we collect all the active and reactive powers from non-controllable devices, or if you wish, all the active or the non-controllable active and reactive consumptions at the distribution transformers. And Y, well, it can be whatever you want depending on the particular tasks that you are after, right? If you are after an SCOPF, as we will see, this is a vector that collects voltage magnitudes, or perhaps power flows at the substation, if you envision these futuristic markets where distribution systems become virtual power plants. Okay? Oh, and I forgot to mention that calligraphic F is nothing but the DC powerful equations. Okay? So now, just to elaborate further, this can indeed be an ACOPF, and therefore the algorithm will be a real-time COPF, or a measurement-based real-time COPF. And in terms of constraints, again, just to hit this point once more, we can add voltage regulation constraints, right? This is for American standards, but I'm sure that in Europe there is something similar. And again, we can also add constraints like this one. For example, if you want to make sure that the aggregate power that is transferred at the substation, P0, is driven close enough to a given set point pk set, that, for example, RTE will ask to utilities, or in this case, California ASO. Okay? You can also add other constraints based on specific operational needs, and in terms of cost functions, is up to you, right? Again, or up to Patrick, of course. depending on what kind of operational needs he has, right? So long as I don't pay much, I'm fine. Okay, so why optimization with feedback? So for a few reasons. So complexity, we are after simple first-order online methods that are computationally light, that can be executed fast, in the order of even a second or sub-second. They can be implemented in distributed fashion, where we share the computational burden across devices, and we eliminate the, let's say, control room, which can be indeed an isolated point of failure. And we also avoid pervasive metering. Why? Because if we need to collect, if we want to really run this algorithm in real time, let's say every second, we need to collect information regarding the non-controllable powers every second for every possible transformer. And if you have 1,000 transformer, you need 2,000 measurements, right? Unless you assume a given power factor, then so this is something cannot be done. Instead of using the map, you leverage the measurements, well, you may have a few measurements that are coming in real time, depending on your operational needs. If you care about voltages in 2 points, you have 2 measurements coming in at every second, right? But also to elaborate further on the distributed implementation, one possible architecture is the following. So you push the decision making down to the DR, where you update the power set points locally, right? Locally, based on your cost function, and also based on the dual variables that are coming from a, let's say, control room of Patrick, and Patrick will basically process the measurements in real time, will spit out the dual variables, and I, user, strike a balance between his needs and my needs, okay? So this is an example of distributed architecture. What else? That's it. Okay, so let us take a look briefly at some numerical results. So first a synthetic data set, and then a real data set. For the synthetic, let us take a look at the, this IEEE 37 non-test feeder. The data set is fairly uninteresting, so we got rid of it, and we utilize real load and solar data from Anatolia, California, close to Sacramento. This is data with a granularity of 1 second. And then we update the PQ set points every 1 second. We update the set points of HVAC system every 5 minutes, so inherently this is actually an asynchronous implementation, which I didn't show the result in order not to be pedantic, but it's stable even in the case. And what we want to do is to enforce voltage regulation, and also we want to try to track some powers here at the substation. So we populate the feeder in a way that if you do nothing, then the voltage magnitudes would have this behavior over the day. Here I just show a couple of representative plots. But nonetheless, you see that for the particular test case that we have, some voltages are going well beyond 1.05, which is the upper limit for North America standards, okay? So of course the inverters here will shut off after 5 seconds, but we let the simulation run anyway. So now we run our online feedback-based algorithm, and we get this behavior. We get this behavior because we encapsulate in a cost function the fact that we want to curtail as less power as possible, and therefore we get this plateau. If we were to encapsulate other objectives, we may not have gotten the plateau, but nevertheless the voltage would have been below 1.05. Okay. Now, in terms of power tracking, let us consider this, let's say, trajectory over this period of time. The red trajectory, we have 5 minute steps motivated by KAISO markets. Then we played around with it with 1 minute steps, and then we also put a consistent ramp. And the black trajectory corresponds to the power at substation that you get using the feedback-based online method. And you see that you are able to track this very, very quickly, again with 1 second update. This is in contrast with a open loop optimization scheme, so without feedback, that is executed at a slower time scale. And of course, you're not able to cope with the variability of the load in solar radiance, which had the dynamics of 1 second as opposed to 1 minute. Okay. So briefly, before I run out of time, this was synthetic data. I know that sometimes synthetic data are not well received. So let us take a look at the real data that we used with Steven as part of the project. We got a real circuit from somewhere, I cannot say where, but in the South California Edison territory. This is a real feeder. The substation is this one. Sorry. That is serving a variety of residential, commercial, and industrial customers. There are some houses here. No, not supposed to say that. I mean, there are heterogeneous customers, right? And even in this case, we run algorithm at the granularity of 1 second for PV systems and batteries. For HVAC systems, again, 5 minutes. Well, what can I say is that here there are 2,000 customers, roughly. So this is a snapshot of the power on the 3 phases, A, B, and C, that we get at the substation of this feeder from 8 a.m. to 5 p.m., 17, if we do nothing, right? If you do nothing. And what we're going to do now is to test the algorithm on this portion here, where, I mean, it's variable, but it's quite smooth, and also in this case here. In both cases, actually, the algorithm works. So as a snapshot, I'm doing exactly the same experiment. I want to track a set point for the power substation on the 3 phases. And so you can see here the red trajectory. They are slightly different because this feeder here was very unbalanced, and the way, I mean, there was no way that we could balance the feeder by using the allocation of the resources that the utility gave us. But you can see that by running the algorithm, you're able to track very nicely all these different trajectories. So even ramps. And by the way, ramps can be very problematic for autonomous controllers that are communication free, right? Okay, here also I told you that I was going to test also the algorithm against this not nicely looking trajectory, and we actually get something smooth. If Patrick gave us a ramp, so if we don't have enough resources, we still have a spike here, but if Patrick gives us some money for additional batteries, we're actually able to smooth it out almost perfectly. So hopefully this can show the value of a real-time algorithm that can, enable fast-acting decision-making capabilities. Okay, so I arrived at the conclusion. So I wanted to tag along and keep talking about time value optimization in this particular talk with a slant of on the feedback, let's say. But the main objective was to leverage this formalism to model optimal operational trajectories, and then try to synthesize and analyze methods that can track these optimal operational trajectories, right? In a way, from a pure theoretical standpoint, this can extend the theory of gradient methods under a time-varying setting, epsilon gradient methods, if you look at errors. Can also capture other applications when you consider fixed point arithmetics, and so on and so forth. Then I try to show you an application in power grids. There are many other applications to talk about. We can talk about that offline, certainly. And I forgot to mention that we also have a real experiment in a microgrid in California where we run these algorithms for 24 hours straight. Now, in terms of questions, there are many theoretical questions to start with. But in terms of implementation, well, one is how real-time is real-time, right? If we want to execute these algorithms every second, then real-time means 1 second, right? And then this means that we need to collect measurement every second, right? And dispatch points every second. It works. Also, Florian showed that it works. Now the problem, the question is how to implement it, right? There is a lot of inertia from utilities to try to even explore these solutions, right? how to integrate this with markets. This is effectively a real-time, this calls for real-time ancillary services markets, right? And again, many theoretical questions, but we can talk about those offline. All right, thank you so much. Yeah.
HVACs are turning on and off, so they're binary. So
Yeah.
then it's not smooth. So how does the theory work?
This is a nice question. So what we do when we have discrete variables, so when you design algorithm, you relax them. So if you have a 0, 1 is from 0 to 1, you build the gradient based on the relaxed problem, and then the solution gives you the probability mass function, right? So you flip a coin. The price to pay is that you may have some infeasibility, so we need to consider a proper restriction of the feasible set in order not to go outside too frequently.
The proofs that you showed don't apply to that case.
No, they do. There is an additional term. So there is an additional term in the bound that accounts for the randomization step, because effectively the trajectory that you are tracking is the one for the relaxed problem. I have no idea how to track the trajectory of the mixing problem.
Follow-up question: what can you guarantee in terms of the comfort of the people that you are turning the HVAC?
Yeah, that one you can put in the cost function.
Oh, you put it in the
Yeah, sorry, I probably went too fast. Sorry about that, but there was a term. Well, I'm not gonna. There is a term that captures objectives of the network, right? And there was the sum of some function that capture objectives of the single customers, right?
Which was a dead band, or what?
Which was what?
The dead band for the HVAC.
That is going to be in the constraint in the set U, calligraphic U. Yeah. Yes, please.
Your example had at the end had some batteries.
Yeah.
I was wondering, is the state of charge in the battery a decision variable in your optimization, or not?
So not here. This is a good point. Very, very good point. So in this case, for the batteries, well, I didn't need to go back, but that's fine. In this case, for the battery, basically, we are assuming that there is you already dispatch the batteries at a slower time scale based on other objectives that you have, and then in real time you try to track as much as possible that predefined set points for the state of charge, while being also able to cope with real-time disturbances. That is basically a two-time scale algorithm connected to what Sean said. We also explore a case where if you look at this problem here, this is a single period problem. So we consider a multi-period problem, and then we implemented the real-time implementation of the MPC, where you shift the window every second. And in that case, the state of charge becomes a decision variable, and
so this is a sub-problem this problem is a sub-problem, a much larger problem.
Yeah. Yes.
What about, let's say, temporal regularization? If you want to minimize actions, you've not looked at that, how it would affect your tracking ability. And I mean, the worst case would be really to say, okay, if I make a decision now, I cannot change it over the next hour or two.
Yeah. This is an excellent point, right? Because these methods are, I mean, I can go back to this.
You assume that you can actuate all the time as much as you want. Right?
No, I mean, so let me make this comment clear. Let me just go to the algorithm, right? So this is effectively a myopic controller, right? Where you try to steer your decisions towards the solution of the different problem, right? So there are two ways to account for what you said. The first step, connecting also to this point, is to consider a two-time scale method, where at a slower time scale you plan, and then the myopic controller tries to follow what you decide as close as possible, right? The other one is to try to use, again, a real-time MPC formulation, where you try to encapsulate temporal constraints. The price to pay is basically the convergence, because the larger is the problem, then the tighter is the bound, and so there is a lot of simulation to be done in that case. The math works, so the simulations is a question mark.
maybe you and Andrea and a bit Florent can comment on how the three things, the connection among these three things. So, for example, can prediction be incorporated in this?
Well, we were talking about this yesterday.
Maybe you can comment on that.
Yeah, this is something that is in the. So, okay, so adding predictions in these algorithms is something that is in the research agenda. It is unclear as of yet where to include a feedback in the prediction or this, right? So that is one point. So to connect to the previous talk, Florian, so let me make two connections. So the first connection is basically this assumption, right? So under the carpet here, there is the assumption that there is a sufficient timescale separation where if I send down the commands, the local controllers are acting sufficiently fast, and as me sitting at the optimizer side, at the algorithm side, I have only a bounded actuation errors or a bounded deviation from the system state had the regulators been converged to the point, right? This is the first connection. The second connection, actually, I think that you already made it, but is when you go down. Let me pull up again the ugly slide. So there are these works here by Nelson Malada, Simpson Porco, and my friend Marcello, where we are effectively considering online algorithms as a feedback controller. So you have a closed loop, the same that he showed, where you also have the dynamics. The problem that we have now is that we were able to prove things only for dynamic LTI, linear time invariant system, and for a very simple class of time varying convex problems, where the only constraint that you have, in fact, is the constraint that for the map, for the linear map. Can you do it for, I don't know, yeah. But hopefully the connection is clear, more clear now, yeah.
Interesting control theoretic classification of the three algorithms we've seen.
Yeah.
Mine was essentially a proportional control with some projection.
Right.
His was a PD control, and yours is a PI control, because dual variable is essentially integrating constraint violation. So it's really a P, PD, PI.
Be careful because you have projections, though.
Yeah.
PID projections are very tough. That's true. That's true. Yeah.
He's right.
Yeah, that's true. That's true.
Oh, it's lag instead of I, yeah.
I'm sorry?
Well, the R introduces like a lag compensator instead of integral. I think, yeah.
That's another good point. That's another good point.
Could you add some sparsity consideration in your framework with some N1 penalization on your control, so to try to have the minimum set of devices you actuate on to reach your tracking capability?
Yeah, this is another excellent point. So you want to add an L1 norm here, right? You want to add an L1 norm here, right? Yeah, so then you make the cost function differentiable. Instead of the projection, you need to use the proximal operator, but that's fine, it works. Yeah, but that's an excellent point. Yeah.
Also, all of these algorithms, no matter which one you take, they at some point need the Jacobian of the steady state map of the system.
Excellent.
Which I guess in practice is the main limitation, because you need to build this Jacobian, collect the measurements.
So
you could estimate it, or you have some idea how to estimate it.
Yeah, so that is correct. So let us take a look at this actually non-convex, the non-convex algorithm, right? So this is the Jacobian on the map, which, for example, in your case, you need to use to build a tangent plane, right? So what you can do here, let's say worst case, I linearize the powerful equations. I can use the fixed point linearization method of Genève or any other method, and then you just play the role of, you just replace this one with a constant Jacobian. That is fine. So what happens though is that so you have an algorithm that is inexact because you have an erroneous Jacobian at every time step, and this will translate into a larger bound in the asymptotic convergence. So if I go to the to this. Here, again, constant Jacobian. Here you had sigma plus E Jacobian, where E Jacobian is the maximum error between the constant one and the true one. Yeah. Does that make sense?
Would be conservative bound, right?
Yeah.
Because in the end, your physics will follow the correct Jacobian.
That is correct. Yeah.
So somehow it's a worst case scenario because in fact you plug there the wrong one, but the physics is going to do the good one. So somehow there is going.
Yeah.
I know that we haven't been able to characterize it, but I mean we have a worst case bound.
Yeah, he's perfectly right. It's a worst case. Yeah.
Is there any particular intuition of why I use this particular regularization and not some other regularization?
Oh, in the Lagrange, right?
Yeah.
Because it was the simplest. And this is actually what I needed. I just needed something that was strongly concave. And this actually goes back to something that, I mean, I didn't invent this regularization, right? This goes back to the, actually, let's take a look at it. I mean, this goes back to Rockefeller in 1975, who showed that this function here, yet simple, has all the sufficient merits that you need to run to come up with an algorithm that is in fact that has a contracted steps. Other people, of course, are looking at other regularizations. If you have a prior on the optimal dual variables, you can actually do lambda minus lambda star prior if you have it. I'm not aware of other regularization.
You interpret it as a price, wouldn't you want to have L infinity or make it as flat as possible so everybody gets fair price?
Oh, you're thinking about the.
Yeah, I mean, lambda is the price. Maybe you want to tie it to how you will want to signal it. If you want to be fair, you will do infinity norm. If you want to make it very unfair, there's one norm.
So honestly, I need something that is strongly concave and differentiable. So it's just a technicality. So it's
So in Florin's algorithm, there's a Lyapunov function, which turns up. I guess it's in the proof technique. But having a Lyapunov function anyway is useful. For example, if you wanted to look at the event triggered scenario, so you don't necessarily want a computer control update at every time instant, but maybe you just want to wait until a certain event occurs. Typically used by evaluating the Lyapunov function, and if it's over a certain value, you update your controller. Is there any sense of a Lyapunov or stability certificate that drops out of your framework?
Yeah, so a couple of comments. So first of all, I apologize, but I didn't provide a slide on the synchronous setting. There is a very similar result for that as well. You just had an additional term because you are missing basically updates of the dual variables. So you have an event triggered. So I believe, and correct me if I'm wrong, but by talking to him, Q linear convergence in a discrete time setting is equivalent to exponential stability in continuous time. So there are similarities. I need to look at the proof. I mean, I'm just thinking loud now, right? But there must be similarities, yes.
There have been proofs of using the Lyapunov function in the continuous setting, at least for prediction correction or tip similar methods. But yeah, as you said, I mean, it's related to Q convergence in the discrete setting.
Yeah.
It's not. I mean, it should come out from the math.
Great time to start. Let's play speaker again.